Welcome to Dependence of Cell Potential on Concentration. So, we can calculate the cell potential under non-standard conditions, and remember that the Gibbs energy change is equal to the standard Gibbs energy change plus RT times the natural log of Q. Q there is the reaction quotient. And now we can substitute in our expression for the energy change, so the free energy change. So delta G is equal to minus NFE. So we can plug that in over here. So minus NFE is equal to then minus NFE naught, because the delta G naught there we can replace with minus NFE naught. And we still then have our plus RT times the natural log of Q. And if we rearrange this, then we get what we call the Nernst equation. So this is E is equal to E naught minus RT over NF times the natural log of Q. And if we change from natural log to log base 10, then we get E is equal to E naught minus 2.303 times R times T over NF times log of Q. And then the Nernst equation can be simplified by collecting all of our constants together and using the temperature of 298 K, because we look on the last slide there. R is a constant, 2.303 is a constant, F is a constant, and if we fix the temperature to a certain value, 298 K, then we can wrap all of them in together with this number here, 0.0592. So now we have E equals E naught minus 0.0592 over N times log of Q, and this now is only true if the temperature is 298 K. That's going to be roughly true for most laboratory conditions. So as long as you're working at roughly room temperature, this reaction is fine. Or sorry, that equation is fine. So let's look at an example. If we have our zinc-copper reaction, where we have the zinc being oxidized and the copper being reduced, and if we have copper ion concentration of 5 molar and a zinc ion concentration of 0.050 molar, then we can plug in our E naught. So our cell potential is equal to our standard cell potential, positive 1.10 volts, minus 0.0592 over 2. 2 here because we have 2 electrons being transferred from the zinc to the copper, times log of Q. Q, remember, was our reaction quotient. So we have our products over reactants, and that then is positive 1.16 volts. So that reaction is spontaneous, and it will proceed until E, our cell potential, is equal to 0. So, what are our concentrations for copper ion and zinc ion at equilibrium? Well, at equilibrium, our cell potential is 0 volts. So we have 0 volts is equal to plus 1.10 volts minus 0.0592 over 2 times log of the ratio between our zinc 2+ and copper 2+ concentrations. We can rearrange this, move this to the other side, this whole term to the other side, getting rid of the negative sign, and then we do some more algebra. We get the ratio there is equal to 10 to the 37.16, which is 1.445 times 10 to the 37. That's a rather large ratio there, which means that our zinc concentration is much, much higher than our copper concentration. But we also know that the total concentration of zinc and copper has to equal 5.05 molar, because we started with 5 molar concentration of copper and 0.05 molar concentration of zinc. So we can then solve for zinc concentration is equal to 5.05 molar minus the copper concentration. That's then going to be about 5.05 molar. And when we plug that in, then we can solve for our copper concentration and find that it's 3.5 times 10 to the minus 37 molar, or thereabouts. Because again, we've made an approximation here. This isn't entirely true. This value really needs to be 5.05 molar minus 3.5 times 10 to the minus 37 molar. To all intents and purposes, this value is correct. It is 5.05 molar. Let's talk about concentration cells. A concentration cell is one whose EMF, the electromotive force, cell potential, is generated only because of a concentration difference. So let's look at a cell with two compartments, each with a nickel electrode, but with different concentrations of nickel 2 plus ion. So one cell has nickel 2 plus equal to 1.0 molar, and the other has nickel 2 plus concentration of 0.001 molar. Our standard cell potential is 0, but the cell is operating under non-standard conditions. We don't have standard conditions because if we go back, here we have a nickel concentration of 1 molar, but there, in this side, we don't have a nickel concentration of 1 molar. So, we're not operating under standard conditions. Our driving force here is the difference in nickel concentration. Essentially, this reaction will proceed spontaneously until the concentration of our nickel ion in each compartment is the same. So, at the anode, this is our dilute nickel. We have nickel solid going to nickel 2 plus ion and 2 electrons. The electrons then go to the cathode, where we have the nickel 2 plus gaining 2 electrons to become nickel solid. Again, the cathode is with our concentrated nickel, so the 1 molar, or initially 1 molar. And if we then use the Nernst equation, assuming that it's at 298 K, we then get E is equal to 0 volts minus 0.0592 divided by the 2 electrons that are being transferred, times log of the ratio between the dilute and concentrated nickel 2 plus concentrations, which initially start out at as 0.001 molar and 1.0 molar, and that means that our cell voltage there is 0.0888 volts. So this is the driving force for that concentration cell. And we can do this with any different or any ions we want, as long as we have the same ion, just at different concentrations. That cell will have a voltage, it will have a spontaneous reaction such that it will tend to drive those two concentrations closer to each other, and until those concentrations are equal, it will have a non-zero cell potential. So that was dependence of cell potential on concentration.